Okay, there it is. Record one. Okay, I think we're recording now. Yeah. All right. Hello, everyone. Welcome to our Intro to Quantum Cryptography workshop. And this is being put on by ACM Cyber in a collaboration with Quantum Computing at UCSD or QCSD. And yes, that's the check and code, as Bryce said in the chat, Qiskitography. Real quick, if you guys aren't yet on the Quantum Computing Discord server, it's a new club. Either Matt or Andy, do you think one of you could put the invite in the chat? So yeah, I'm assuming since you guys are here in week 10, you're either interested in quantum computing or you're already in the club. So yeah, there's the invite link. Okay, so let's start. Now what we're going to do today, first, I'm going to remind you a little bit about how encryption works normally, and then the problem with what classical encryption might encounter. And then we're going to go into how quantum cryptography works. And then towards the end, we'll have a hands-on example presented by Matt about a quantum key distribution algorithm. Okay. So now how encryption works generally. The idea is you need a message and you need to turn it into a cipher, something that is unreadable except to you and the person you want to send a message to. So what you need for that is a key. The key turns the plain text into ciphertext. And in symmetric key encryption, the same key also turns the ciphertext into plain text. With asymmetric encryption, you have a key that can turn plain text into ciphertext, but that same key cannot turn the cipher back into plain text. For asymmetric encryption, you have what's called a private key that you keep with yourself so that you can decrypt it. And asymmetric encryption is what's used most often because it's a lot safer to have a public key and a private key scheme than it is to have just a single key scheme. Because if you only have a single key scheme, then you're going to have to figure out a way to share that key with the person whom you want to read your message. And that's not always secure. Keep in mind that problem because that's going to become relevant for our quantum cryptography. Now, what exactly is a key? Well, to put it simply, their keys are numbers generally. And what you do with it is you cross it with your message to get out the ciphertext. And this would depend on the encryption scheme. So as a very basic example, if we wanted to encrypt the number, the word hi, first we need to convert it to a number. And let's just convert it to 8, 9, because H is the 8th letter in the alphabet and I is the 9th letter. Then what we can do to encrypt this, for example, is we can multiply each of those digits by 5. And then you'll get 40, 45. In this case, the key is the number 5. And you're multiplying the numbers of the plain text to get the ciphertext. You can also use that same key to get back the original message. You just divide those two numbers by 5. So this is the very, very basic encryption scheme. Now, for modern encryption, it requires the product of two really big prime numbers. And these prime numbers require up to 2048 bits. So prime numbers on the order of magnitude on the order of 2 to the 2048. So really big prime numbers are required for modern encryption. You need the product of those two numbers, n, to generate a public key. And then to generate a private key, you can do that with n, but only if you know what the two prime numbers were. So this would be an asymmetric encryption scheme. What it depends on is that you can generate two really big prime numbers and generate the product of it, but it's really hard for anyone who just knows the product to be able to factor it and get the two prime numbers. For classical computers, this takes such a long time that it is not going to be possible for you to break an encryption like this. Okay. Okay. Okay, so before we move on, does anyone have any questions about what I've said so far? Hi, Annie. Okay, if there's no questions, I'll just move on. So now we're gonna get into the quantum stuff here. So let's have a poll. I did set up a poll here. Let's launch that. Right, so how much do you know about quantum computing? Waiting for the results to come in. Oh wait, someone here is Peter Shore. It's me. Okay, that's everyone. Those are the results if you wanted to see it. Is it possible for me to see who Peter Shore is? Okay, raise your hand if you're Peter Shore. Huh? That's weird. Okay, so we have an anonymous Peter Shore. Oh, there's Peter Shore. Look, say hi in the chat, Peter. Big fan. We're a big fan. Okay, so look, Shore, that's your algorithm right there. So now the problem we have with classical encryption techniques is that I told you that this prime number we had earlier is really hard for a classical computer to factor. Well, it turns out for quantum computers, that's actually not so hard. With an algorithm like Shore's algorithm, or there's some other algorithms out there, a quantum computer can actually do this much faster than a classical computer can. So in the future, if we have usable quantum computers, someone might just be able to break an encryption whenever they want. Just it might take a few minutes maybe on a quantum computer. And obviously that's not going to be very good because nothing is going to be secure anymore. So we're going to need a solution for that. And that solution can also be provided by quantum computers. So before we move forward with how quantum cryptography works, I'm just going to go over some basics you might need to know about quantum computing. Okay, so the first one, superposition. Now in a classical computer, you have these bits, right? And a bit can either be in a 1 or a 0 state. It is definitively a 1 or a 0. So if you write a 1 into your memory, then you know it's going to be a 1, even if you leave it for a while. And then when you come back to it and you read it, it's still going to be a 1. A qubit, however, has a very unique property. You can put it in what's called a superposition of a 1 or a 0. So when you leave it in a superposition of a 1 or a 0, when you come back to read it later, it's going to collapse into either a 1 or a 0. It is probabilistic, not deterministic. And this is, and yeah, so if you can see, there's some complex math that goes on behind what a qubit can do, which I'm not going to go over.
Oh, look.
Did someone say anything? By the way, Matt, feel free to jump in if you want, if you need to add anything.
Yes,
There you go.
I got you.
Okay, cool. Okay, so that's superposition for you. Now, polarized light. Peter Shore face reveal. Yeah. Polarized light is going to become important in quantum cryptography, and I'll tell you about it once I go over this. So light, as you might know, can be represented as an electromagnetic wave. And that light waves in a certain direction. So if you can see in this picture, it waves, there's light that waves up and down, and that blue wave goes left and right. Yes, brush up on your wave optics. Okay, now you can, you can measure the polarization of this light via a filter, as you can see in this image. You can, as you can see in this image, with that polarizer, only vertically polarized light can go through, while horizontally polarized light cannot. So here's how that works. Suppose we have photons that are polarized vertically, horizontally, and diagonally in these two ways. So diagonally left and diagonally right. Now, we have two different types of filters, a vertical filter and a diagonal filter. When we put a vertically polarized light through a vertical filter, let's say that gives us a 1. And if we put a horizontally polarized light through a vertical filter, let's say that gives us a 0. Now, same kind of idea with a diagonal filter. If you put a left diagonally oriented photon of light through a diagonal filter, that'll get us a 1. And light polarized in the other direction, gone through diagonal filter, will get us a 0. So now what do you guys think is going to happen if you send vertically polarized light through a diagonal filter? Just want to ask, anyone can answer. If you know the answer or if you want to guess. Okay. Yeah, okay. So Michael is right. What you're going to, if it's 45 degrees short, yeah. Yeah, that's what we're assuming here. Just to simplify it, the vertically polarized photon is 45 degrees with respect to the filter. So yeah, Michael's right. You're going to get a 1 with a 50% chance and a 0 with a 50% chance. So if you make a measurement of this, you're going to get either a 1 or a 0, and each of those is going to be equally likely to occur. And as you can probably guess, the same if you input a diagonal photon into a vertical filter. You're going to get a 1 with a 50% chance and a 0 with a 50% chance. Okay, so now that we know that, does anyone have any questions about that so far before I move on?
So I wanted to mention, it might look like all there is to it is some of the light is diagonally polarized and it just kind of sneaks through, but there's more to it than that, right? It's not just like it's diagonally polarized and so it kind of just creeps through halfway. in a classical sense. It's actually in a superposition. And Ishan will talk about this later, right?
Right. Yeah, actually, I should have talked about that. So remember, I mentioned the concept of superposition earlier. That is exactly what's happening when you are measuring vertical light with a diagonal filter, for example. It can be treated as if the vertical light is in a superposition of being left diagonal and right diagonal. So putting it through the diagonal filter makes a measurement on the photon of light, collapsing it to either diagonal left or diagonal right.
And so we might ask, suppose you have light pass out of a lamp and you pass it through a vertical filter. And then after that, you pass it through a horizontal filter. How much of the light would get through if you had to guess? Anyone?
I think someone's talking, but we can't hear.
Oh shoot, I've been unmuted the entire time.
There you are.
Okay, no takers. But sort of as you might expect, if you pass your light through a vertical filter, then all the light will be vertically polarized. And then if you pass it through a horizontal filter, then none of the light will pass through. It'll be basically completely blocked because the vertically polarized light cannot pass through the horizontal polarizing filter, right? So that's normal. But there's a really cool trick, and I promise you this is real. You can look it up. Is if you have a horizontally polarizing filter and a vertically polarizing filter, then no light goes through. But if you put another diagonal filter in between them, light will go through. For now you'll just have to believe me that this is real. But basically, it's slightly counterintuitive, right? You have one dark lens and you have another dark lens, and you put a third dark lens in between the two, and the light gets brighter. And the reason that this works is that diagonally polarized light is a superposition. So it's not just like it's not just that you twisted the light. It's actually diagonally polarized light is actually a combination of vertically and horizontally polarized light. And that means that if you actually pass light through a diagonal filter before you pass it through the horizontal one, then some light does get through. And that's what we're seeing with polarization. So polarization is a form of superposition.
Oh yeah, Annie just posted a Minute Physics video. Minute Physics did make a good video about this. I think. Yep, thanks. Okay. So if there's no other questions, let us move forward. Okay. So now how quantum key distribution actually works. Well, I told you at the beginning that when you have a symmetric key encryption scheme, you're going to run into the problem that you have to actually get your key to other people, right? You need to encrypt the message, but also the other people need to decrypt the message. And I told you that that's hard because how are you going to get to someone securely? Well, with quantum key distribution, you could do that. On paper, it is perfectly secure. And I'm about to explain why. Okay, so let's say we have our two characters here, Aaron and Sharon, and they want to communicate with each other securely. But this guy, hacker man over here, he wants to listen in on what they're saying. So Aaron needs to get a key over to Sharon. But how's he going to do that without hacker man interfering? Well, here's one thing he could try. He could send photons of light one by one over to Sharon, and she could measure them like this. So Aaron sends a vertical one and then two horizontal ones. And then when Sharon measures it with a vertical filter, she's going to get 1, 0, 0. And they could use that for the key. But here's the problem with that. the hacker might be able to, if the hacker knows that only vertical filters are being used, then he or they might be able to interfere and make measurements themselves and get the key. And so we don't want that. Aaron's going to have to mix it up a bit. So let's say he also puts diagonally polarized photons as well. And that's going to be better. So this time you have to use a vertical filter and then a diagonal filter and then a diagonal filter to read this. And then what you get out is 1, 1, 0. Now the problem with this is Sharon actually can't know what filters she needs to use, because if Aaron and Sharon were to somehow communicate which filters to use, then it's also possible that the hacker man could intercept which filters they're trying to use and then use those filters himself. So realistically, what's going to happen is Sharon is going to have to guess which filters to use. So on the first one, she guesses correctly and she gets out a number. On the second one, she doesn't guess correctly and she's going to get a 1 or a 0 with a 50-50 chance. And they are actually going to have to discard that value, but as it turns out, it's perfectly fine. In fact, it's part of what makes the encryption scheme secure. And I'll explain that later. So in this case, the value for the key they're going to get is 1, 0. Now, here's how they can all put it together. Aaron randomly generates his polarized photons, sends them over to Sharon 1 by 1. Sharon measures them all, but has to make guesses on which filters to use. And she gets these values out, okay? Now is the point when Aaron shares which filters he used across to Sharon. And then they communicate with each other on which filters were the bad filters. So they discard those ones. So now in this case, both Aaron and Sharon now know that they have to discard photon number 2, photon number 4, and photon number 6. And now that they've done that, they've got a string now, 1, 0, 0. So that's their key, 1, 0, 0. Okay, but now let's look at what our hacker man might try to do. Remember I told you Sharon has to guess which filters to use? Well, since the hacker man doesn't know which filters Aaron used either, he also has to guess. And so let's say Aaron sends over a diagonal photon, and the hacker man tries to intercept it and measures it with a vertical filter. He's going to get something. Maybe it's a 1. But then when the photon gets to Sharon, there's actually a way that both Aaron and Sharon will be able to tell that the photon was intercepted, that it was measured. And now that they know that the photon was measured, they can actually decide, we've been compromised, we have to try this again. And so now the hacker man doesn't get anything useful out of this. Even if he were to be able to intercept all of them, he would also have to guess which filters Sharon used. So he can't feasibly do that for a long enough key, right? This is only 6 digits, but realistically, it's going to be a much longer one. And how is the hacker man supposed to guess the right filters to use? And then on top of that, once Aaron and Sharon know they've been compromised, they're just going to toss away this key and try again. So that's why this encryption scheme is secure on paper, because any attempts to get the key while in transit is going to fail. Okay, so does anyone have any questions about this? And Matt, do you have anything to add?
Yeah, I wanted to say, so remember how we mentioned how putting that filter in between changes how the light goes through. That's essentially what a hacker is doing. Because they don't know what bases Aaron, in this case, sent his photon, they don't know what bases to actually measure it in without collapsing the state. And so inevitably, they collapse the state. And so then the person receiving the qubit knows that it's been collapsed, and they know that they've been spied on, and they know that they have to find a different way to transmit their message. So that is sort of the same process that you see with polarization filters in your sunglasses, is the same principle that you see here in a quantum key distribution system.
Yep, exactly. Okay, so some questions in the chat. What happened to Alice and Bob? I killed them. Maybe it's minute as in small. Where is that from, Chris? And then Samuel asks, in this case, the key is the sequence of differently polarized light. Yeah, so yeah, once you make the measurements of those, the final key is the string of digits that you get. Yep. Okay, are non-45-degree incremented filters more or less secure? Matt, do you know about that?
Yeah, non-45 are less secure, specifically for the reason that, remember when we have a 45-degree incremented filter, it's exactly in between vertical and horizontal, right? And so if you measure it, there's a 50-50 chance of it collapsing. If it's non-45 degrees, if it's closer to one or the other, then statistically, the person who is spying should always, especially if they know that, they should always measure in one basis, right? So if your filters aren't 45 degrees, say it's like 20 degrees from vertical, the hacker man should always measure in vertical, and then he'll have a much higher chance of guessing correctly and actually spying on you without you noticing. So 45 degrees is perfect. Anything less or more than that is actually easier for the hacker to intercept.
So in this example, what were the filters Aaron used? So Aaron used, well, to generate these photons, he used something vertical, and then diagonal, horizontal, diagonal. I didn't go into the details of that, but what he's doing is he's trying to generate one, what did I call that? The 0. Yeah, he's trying to generate the sequence 1, 1, 0, 1, 0, 1. And this is just how they're represented in photons of light. And then once he passes that information over to Sharon, I should also add, it is possible for the hacker man to intercept Aaron's message when he's telling Sharon which filters that she was supposed to use, and that is also going to be fine, because even if the hacker man does know that, it's unlikely that he was able to guess the same filters that Sharon used, and so even if he knows which of his numbers were wrong, if he discards those wrong numbers, he's not going to have the same number.
To address, I think when Annie's asking about using the wrong detector, like using the wrong polarization to measure, and that is correct, completely correct. So Bob will only, or sorry, not Bob. What's our receiver's name in this case?
Sharon.
Murdered Bob. Sharon.
Aaron and Sharon, yeah.
Sharon and Sheridan.
No, gotcha. Aaron and Sharon.
Sharon, perfect, thank you. So in this case, Sharon is only going to measure in the right bases 50% of the time. It's not going to happen any more or any less, because Sharon is basically guessing vertical or horizontal, or vertical or diagonal. And only 50% of the time will that actually be the same as Aaron's basis.
Okay. Someone asked, how does Aaron learn the key 100? So when Aaron and Sharon are communicating over which filters that they were supposed to use, both of them now know which ones Sharon was wrong on. So they now both know which of these to discard. Okay, let's see, what other questions? There's a possibility that you used the wrong detector. I don't know what that is in response to. What is the message he is sending? Okay, so Tony, right now, Aaron is not sending a message right now. He's sending the key. After they have their key, they can then send whatever they want to each other. But they haven't sent anything yet. Maybe he'll send something like I don't like sand.
And someone asked how to tell if you're being spied on. So specifically, in this case, you interpret error in any way as being spied on. So you can see here, like this, the final string in this example is really short. But what they would do is Aaron would publicly announce some of the bits of his final string. Like he would literally over the radio or over a public channel, or possibly an unencrypted channel, actually say, for instance, my last bit is 0. And then Sharon would also reveal her last bit. So she would say, my last bit is 0 or 1. And if they're different, then they assume that they're being spied on. Because the only way that if somebody was spying on them, their measurements would have messed up this whole process and would have introduced bit error. And so what Aaron and Sharon do is they actually reveal part of their key that they end up not using. They have to throw that part away over a public channel. Compare if it's the same, and if it's not perfect, then they do a little bit of stats and decide whether or not they're being spied on. But the stats works out.
Again, I'm using very short strings in this example, but in a real situation, there's going to be a lot of digits going across. Like I told you, modern encryption uses 2048-bit encryption or even higher numbers. The length of the key is going to be maybe that high, I don't know, but it's going to be really long because the longer you have it, the more secure it's going to be. Okay, so yeah, that was Seth's question. Are there natural ways that error could be induced in photon transit? So yes, actually. Remember when you use a filter on a photon, what you're doing is you're making a measurement on it. What could potentially happen is a photon in transit could hit anything, and then it could be accidentally measured. And so that would be bad. You don't want that to happen. And so when you're sending these photons across, you have to make sure that the channel you're sending them across doesn't have any sort of like errors in it.
Yeah, so part of your statistical analysis is that you estimate the errors in your channel, what they should be. So actually, for instance, if you're doing it over free space, you just have a laser pointing at a satellite, then you estimate the amount of errors that you should get from natural errors. And then you actually do this part where you compare the predetermined part of your key, and you see if the errors are more or less than that. And if they're less than that, then you're good to go. And actually, after you've done that, you can actually do a classical error correction algorithm to get rid of the noise in your channel. But of course, if your noise or your errors are more than what you expect from your channel, then you know that you're probably being spied on, and you should find a different channel.
That was sufficient motivation for you to finish the assigned reading for Ling 17. You're welcome. Is Ling 17 the cryptography one?
Yeah, it is.
Yeah, okay.
We're reading the code book. And there's a section on quantum cryptography at the end. So
Ooh, nice.
it's not bad. You guys should all read it.
You know, actually, funny coincidence. Today in my Math 103A class, which is Intro to Abstract Algebra, so it's about group theory and stuff. Today was a special topic lecture, and it was about encryption. So that's fun. Our professor did briefly mention quantum computers, but just briefly because it wasn't super relevant, but still an interesting lecture, I thought. Okay, do spying errors cause a cascade in the bits read after the spying, or does it only affect the bits that were attempted at being read? Let's see, so I think it would only affect the bits that were attempted at being read. But you'd still need the entire string of light. And if someone only intercepted a few of the bits, then it wouldn't help them very much because they'd only have those few bits, not the entire key. Okay. Yeah, let's just see if there's more questions. Post a link to what? Oh, that, yeah. Okay. Yeah. Math 187A, crypto. Thanks. I think there's also a CSE class about cryptography. Is it CSE 107? Forgot which one. Yeah, CSE 107. So yeah, like Catherine said, Math 187A, if you're interested in cryptography, you can take that. CSE 107 also there. CSE 107, yeah, I think it's major restricted. Class material. Well, if you're Math CS, you can do it. You just have to submit an easy request and they'd have to approve it. And contrary to the name easy, it's not that easy to get accepted. It depends on how popular the class is. Yeah, you could also always do extracurricular reading. Yeah, that's the annoying thing about Math CS. First of all, you don't get priority. Second of all, major restricted classes, pain. Okay, so if there's no more questions, I think we can move on to the hands-on example. Yeah, demonstration time. Okay, so Matt is now going to demonstrate this algorithm.
Yeah, so I have posted a Jupyter notebook file in the chat. So if you want, you can actually open this in Jupyter Notebook and follow along. And I will also share my screen to show you through this. So, okay, let me do that.
Yeah, all participants can share. So you should be able to share now.
Okay, perfect, thank you. Okay, bam, and you can see my screen.
And if you guys want to follow along, let me copy this link. Don't have Python on this computer. Okay, you don't actually need to run it on your computer. What we used was this site, cuberate.com. You can, maybe if you want, you can spend a few minutes to set up an account for it. It's basically like Jupyter Notebook. You can open up something like this and then run this file on it.
Would you like me to go through very quickly how to do that, Ishan? Or should we just go ahead with the demo?
Okay, so for everyone in the call, do you guys want to set up the account yourself so you could try it yourself? Because if so, then we can show you how to set this up. Is there anyone who wants to? Demo time.
Okay, let's.
Are there any technical steps in signing up? No, it's just signing up for an account. It is going to take a few minutes.
Okay, let's do it. Because QBraid is really useful for quantum computing stuff. And if you're interested in quantum computing, then a lot of our QC programs will be in the QC club will be through QBraid. So if you're interested in signing up for QBraid, just go here with this is qbraid.com. And all you need to do is sign in. I might be already signed in, so I should log in. Am I already signed in? Yeah, let's sign out. Okay, there we go. And then you just make an account. And let me see. I should not have logged out because I forgot my password.
GG.
Okay, and then once you're in your QBraid portal, it's best to go to learn.qbraid.com and then the QBraid environment. And they have an internal server error. That's not good.
Wait, what?
That's not good. I think QBraid is down. Crap. Yeah, QBraid is down.
Error.
Okay. Oh, no. So if you want to register for QBraid, it doesn't work for you?
It works for you?
Actually, I'm also able to log in, but once I go to learn.qbraid.
Yeah, so go to learn.qbraid and then select the QBraid environment. Does that work for you? Wait, that works for you?
Oh, okay. Well, that's great. Then I guess just my thing just is broken. But once you've entered the QBraid learning environment, it should look somewhat like this. It's basically just a Jupyter notebook with a big thing on the left-hand side. And what you want to do is there'll be an Oh, okay, it's broken.
Yeah, the environment is broken. Yeah. Okay, so yeah, it is down.
Okay.
You were able to see QLearn. Yeah, I think. Yeah, learn QBraid, right? You click on that, then you go into the environment, and then it just doesn't work currently, it looks like.
Yes, they do. Servers unavailable. Okay, well.
That is.
Maybe one day QBraid will fix their website. Until then, let's just go through like this. So if you have Jupyter Notebook set up on your computer, then yeah, feel free to open that IPYNB file. If not, then I guess we can just go through here. Okay, Ishan, do you want to start?
Yeah, go ahead and start explaining.
So here is the code.
Is your screen frozen? Looks like.
Can you see full algorithm? Still frozen? Darn.
Are you moving around? Because I don't see any moving.
I'm now moving.
Yeah, it's frozen.
Damn. The technical difficulties are not.
Technical difficulties are technical.
Yeah. Okay, now?
I see a black screen. It says Peter Shore has started sharing screen.
This is not good. Okay, any luck?
Wait for it. It's still showing a black screen. I'm just thinking maybe if we wait.
Might. This is interesting. I have like 500 gig internet. I don't understand why this is not working.
Wonderful.
This is not good at all. Now? Nothing?
Still black.
Ishan, do you want to share the file?
Okay. Let me try. I'm gonna try signing in, but if I can't load the environment, then it wouldn't work, right?
Yeah, do you
Okay,
have
so
a
I'm
notebook?
Jupyter Notebook. Do I? Oh, I think it's working now. I can
Oh,
see your screen.
okay, great. Can you see the words of the whole algorithm?
Yeah.
Okay, fantastic. Okay, nice. Okay, so yeah, fantastic. So whatchamacallit, Qiskit is a Python package. It's just a Python library. Basically, programming in Qiskit is very similar to programming in Python in general, and there are just a few specific functions and a few visualization things, and that's about it. So you can see that basically all we're doing at the very top is just importing the Qiskit quantum circuit, the backend, which is a quantum simulator, and some random number generators for this. So down here on the bottom, the whole algorithm is what Ishan described. So in the very beginning, Alice just generates random bits. So that's this np.random integer between 0 and 1. And both Alice and Bob generate random bases. So you can see here that Alice is generating random bases and Bob is generating random bases. In this case, the bases are either 0 or 1, which corresponds to vertical and horizontal for 0, and the two diagonals for 1 are the two bases. And then essentially, what Alice does next is she encodes her message. So she puts each bit in the corresponding basis. So if it's a 0, then it'll just be a 0. But if, for instance, she has a 0 in the diagonal basis, then it will be diagonal this way. Or if it's a 1, it'll be diagonal this way. Then Bob measures them, and then Bob measures them, and we can sort of go through how that works. So going up a little bit, the first step is that Alice encodes her message. So here you can see we have the bits and the bases. Both are just a random string. And all we do here is we declare a quantum circuit. This is very simple, but basically we're just saying that, hello, Qiskit, I need 1 qubit and 1 register. And then she prepares each qubit. So this is saying basically if our bases is 0, that means we're putting it in the vertical and horizontal basis. And then if our bit is a 0, then a qubit in Qiskit in this Python library is 0 by default, so we don't do anything at all. And if it's a 1, then we flip it. The X gate is a flip. So this first part of the code just says, if we're encoding in the vertical horizontal basis, then if we're trying to get a 0, then we leave it the way it is. If we're trying to get a 1, then we flip it from vertical to horizontal. And then if we're preparing a qubit in this basis, in the diagonal basis, and which we get from having a 1 in our basis string, then if we're looking for a diagonal 0, which is say diagonal this way, we apply a Hadamard, and the Hadamard will take us from here to here. Applying a Hadamard is like putting a diagonal filter in. So if you have vertically polarized light, you put a diagonal filter in, and then that becomes diagonally polarized. And so we're saying if we want to encode a 0 in diagonal basis, we put a diagonal polarizer in it, and it goes diagonal. If we want to encode a 1, then we flip it from vertical to horizontal, and then we do the same thing. And by doing the same thing, then we have the opposite diagonal. So actually, does that make sense here so far? What we're doing is we have bits and bases. Bits can be 0 or 1, bases can be vertical and horizontal or diagonal, and we are encoding each bit in each basis.
Yeah, so there's a question, Samuel, what are the plus and minus states? So that's another way to represent which direction that this light is polarized in. So what we used, what I said when I was explaining this was there was a horizontal or vertical photon, and there was a left diagonal or a right diagonal photon. You could also call that a plus state and a minus state.
That's right.
Is that right, Matt? Yeah.
So a plus state is a diagonal photon. Say it doesn't actually matter in this case, but say it's a like this diagonal photon, and a minus would be this one. So a plus state is a diagonal photon, and the minus is the opposite diagonal photon. So the first thing Alice does after she generates her random bits and her random bases is she just encodes those bits in those bases. And so that's what we do. Then Alice sends those bits to Bob. So she does not tell him what they are. She does not tell him what bases they're in. Alice does not tell him to measure vertical or horizontal or diagonal. She's completely quiet about that. Bob has generated the bases already. He generates his random bases, and then he receives the message and he measures them in that basis. So for instance, suppose Alice sent him a 1 in the vertical basis, well, a vertical horizontal basis. So a 1 in the vertical horizontal basis would be vertical. And suppose Bob is measuring in that basis. Well, then he checks, is it vertical or is it horizontal? And since he's checking in the same basis as Alice sent it in, he gets the right answer. So this kind of makes sense, right? If Alice sends a vertical bit and what's his name, Bob checks, is this vertical or not? Then if they send and measure on the same basis, they're doing really well. That means they got the right bit. However, if Alice sends in the vertical horizontal basis and Bob measures in the diagonal basis, then they might get an error. They might get the same result, but they might get a different one. So that's what this measurement process is. Bob takes his bases, he takes the message, and he measures the message in his bases. Does that make sense? And Ishan, would you like to add anything?
I don't think so. I think you've got it covered.
And so, as you kind of might be able to guess, because Bob doesn't know which basis he should ideally be measuring in, he only measures in the right basis 50% of the time. He has a 50-50 chance of guessing the right one. And so that's what this does. So now Alice has sent all of her bits. Bob has received those bits, but half of them are wrong because half of them, or actually not half of them, like a quarter of them, because half of them he measured in the wrong basis. And when he did measure them in the wrong basis, they had a 50-50 chance of getting the right or wrong answer. So there's a 50-50 chance of him measuring them in the wrong basis. And if he measures them in the wrong basis, there's a 50-50 chance of them actually turning out to be wrong, sort of accidentally, as opposed to accidentally turning out to be right. And so overall, there's a 25% chance that his bit is wrong. And so what Alice and Bob do then is, over a public channel, over a channel that anyone can spy on, they both announce their bases. So Alice says, I sent all my bits in vertical, diagonal, vertical, diagonal, vertical, diagonal, vertical, diagonal, 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 vertical, whatever, it's random. And Bob says, okay, I measured them in the same bases, only like the second to last one was vertical instead of diagonal. And this other one was diagonal instead of vertical, and so on. So they're different at some point. And basically, once they've compared their bases, they know which ones they sent and received in the same bases and which ones they sent and received in different bases, right? And actually, because they've announced this over a public channel, the whole world, you can basically assume that the whole world knows this, but it doesn't matter because they don't actually have the measurements. So once they've done this, Bob knows that he measured, 5 or so of his bits, 5 out of 20 of his bits wrong. They actually delete those bits. So you can see here that they just add the good bits they keep track of the good bits, and then they just return the good bits. So they trash all the ones that were sent and received in different bases. And once they've done this, then they know that ideally their two keys should be the same. So this is basically the goal of the whole thing, right? Key is random, but they know that they should be the same. Alice and Bob should have the same exact random string of ones and zeros that they can use to encode their message. However, they might be being spied on. And so what they do is then they take a chunk of their bits. In this case, these are the sample bits. So we have the overall bits, and we have the selection, and the selection might be take the last 10 bits. And then they both actually reveal those bits. So literally over the radio or a public channel, Alice will say, the end of my key, of my secret key, the end of my secret key is literally 10110011 or something. And Bob will do the same thing. And they compare if those two numbers are the same, because they know that in an ideal world without error and without spying, those numbers should be exactly the same. And so once they've compared them, they actually look and they calculate the error rate. And specifically, they calculate it if it's above a certain threshold, the threshold that they expect from noise in their channel. And if it is, then they assume that they're being spied on. And this is actually extremely likely. But if they're not, if the error is actually lower than they expected, then they're fine. And although they might still have error in their actual string, they can apply a classical error correction algorithm to get rid of those errors until they're confident that they have the exact same key. And actually, part of the whole revealing this answer and error analysis part is figuring out whether that classical error correction algorithm will work. If there's if there are sufficiently few errors to run the classical error correction algorithm. Yeah, so that's that. And once they've done that, once they've compared whether there are sufficiently few bits, then there are two options. A, there are way too many errors. Then they're being spied on. They have to throw this away. They have to find a new channel. Or B, everything is fine and they have the exact same string and they know that they haven't been spied on. Yeah, it's a little bit of a statistic. Yeah. Now, if you're being very careful, then you might figure out actually that, like, if the person spying is extremely lucky, they might measure in the wrong basis and measure the right result. So actually they might measure in the diagonal basis and then have a 50-50 chance of getting horizontal or vertical, and they might actually measure vertical and get the right result every single time. And that would be good, actually. If that would happen, then they could actually spy on Alice and Bob without Alice and Bob knowing. But because these measurements are perfectly random, because of how quantum superposition works fundamentally, and also because actually, like Andrew mentioned, the 45 degree, there's actually 45 degrees between the vertical and the horizontal, as opposed to fewer degrees. It's perfectly random. And so you know that if you send a certain number of bits, like a lot of bits, like, I don't know, 100, 200 bits, and in practice, it would be actually much more, then you know that it is statistically impossible for them to spy on you in this case. And so the algorithm, in a sense, is perfect. You cannot crack it. You cannot crack quantum key distribution with a really powerful computer. It's impossible to do it that way. If you want to actually crack this sort of algorithm, you have to like hack the laser of the person sending this, or hack the detector. And so obviously, like, this doesn't destroy the field of cryptography, but that's a lot more complicated than just having a really powerful computer and factoring a key. Yeah, any questions? Ishan, do you want to add anything?
No, I don't think so. I think, can it be run now, or is the server still?
Yes, it can be run. So here I ran the import statements. Here I just declared the functions. Yeah, and then there I just ran the full algorithm. So it generated random bits, generated random bases, generated bases for Bob. And so here you can see Alice's bits, and this is actually Alice's bits is what she's sending. And then Bob here printed his results. And so you can see that these are actually not the same. So a lot of them are the same. You know, we have 0, 1, 1, and also we have 0, 1, 1, but this is already a 1 and this is 0. So we have an error there between Alice's bits and Bob's results. Then what happens is we actually remove the garbage, right? So so they're comparing the bases. Then they figure out for which bits the bases are different, and they actually remove that. And so now you can see if you compare Alice's key to Bob's key, they're exactly the same. So we also have the same 0, 1, 1, but the next one is removed. So, or the next difference is removed, right? So this bit is removed because here it was a 0, here it was a 1. So we get rid of that. We switch, we move on to the next 1 here, and so here that's a 1 and a 1. So after this remove garbage step, Alice and Bob have the same key. And then what they do is, you know, they've decided on a sample size, and they reveal their samples, and then they compare their samples. So you can imagine this is being announced over the internet or the radio or an unencrypted channel. And then, you know, they check, are their samples the same? In this case, it's true, they haven't been spied on. And so then they know that their key is the same. And that's how the whole algorithm works. And so over here, we have just a chart that demonstrates, yeah, knowledge, and then, you know, Eve, our eavesdropper, and Bob. Yeah, and so in this case, you know, Alice has her bits and her bases. Bob only knows his bases. Alice sends her message over to Bob. Bob measures it, and he knows it, and he announces his bases. Alice announces her bases, and Bob also announces his bases. Then they can get rid of the trash, and they have the same key. Then they announce the samples and check if the samples are the same.
Okay.
And yeah, okay. So yeah, once again, they don't announce their actual bits until they're doing the sampling part at the very end. They do announce their bases. They're for everything. They announce their entire bases. Michael's analogy is close. It's close. So Michael mentioned that, you know, is this a good analogy? They're trying to figure out, they're trying to find the right filter set. Almost. So it's, I would use a very similar analogy. So specifically what I would say is that Alice is trying to send, yeah, some random bits to Bob, but she's trying to send them precisely. So she, yeah, then she has a set of filters, you know, two filters, and she is randomly sticking those filters in front of the flashing light, you know, just randomly switching them out and so on. Bob is on the other end of the system, you know, in the other house, looking at the lamp. Bob, it also has two filters, and he is also randomly sticking them in front. But after they've done this, you know, Alice pulls out a loudspeaker and screams, you know, at 12 o'clock, I sent you using the green filter or using the vertical filter. And Bob goes, oh, okay, I also measured using the green filter. That means that word was correct. And
that one digit.
That one digit. In this case, actually, not even digit, that one bit was correct. And yeah, and then if they measured, if Alice sent with, you know, a vertical filter and Bob received with a horizontal, then it's wrong. And then, you know, Alice and Bob both, again, over the loudspeaker scream, you know, did you get 00111? for at the end, at the very end. And if Bob says no, then they're being spied on. Someone else is sticking another filter in between.
Okay, so I just sent a feedback form in the chat about this workshop. So if you could fill that out, that would be great. We love data.
And if you have a question, please ask.
Yeah.
Because, yeah, I'm sure other people also have your question. It's probably just me not explaining stuff well.
Yeah, we will sit here for questions. In the meantime, if you're not already in the QCSD or quantum computing at UCSD Discord server, there's the invite link for that. Aaron, okay, so we're not selling your data because it's not profitable to sell data. It's actually much more useful to use data. What we're doing is using your data to get a profile on you so we could send targeted ads at you. And that's much more profitable than selling it, so. I'm gonna stop recording now.
And I can stop screen sharing actually, unless someone.
Yeah.